This is Lab 4 Circuits for Physics 2212. The purpose of this experiment is to predict the behaviors of circuits containing resistors in series and in parallel and examine the behavior of ohmic resistors and capacitors. There are going to be three main principles used throughout this lab: Kirchhoff's node rule, Kirchhoff's loop rule, and Ohm's law. And these are all going to revolve around the same law of conservation of energy. The amount of energy that you put into the system is going to be the amount that you get out. You cannot create or destroy energy. So this is our first setup here, where we have 3 volts of coming from our batteries, and we have 2 resistors totaling in at 147 ohms. The predicted amount of amps that are running through this system is 0.0204 amps, and this is coming from Ohm's law. This is the amount of amps that we see in this system, and the current is going to be the same at any point in this system. It doesn't matter where you put the ammeter, and this is because this system is in series, so the amount of current running through the system stays constant. Now let's take a look at different pieces of this system. We can see that Kirchhoff's loop rule is upheld here. The sum of the potential differences equals 0. We are beginning with 3 volts, and then we have 2 resistors that take away from that change the potential difference, one being negative 0.959 and one being negative 2.041. At any point in this system where there is no resistor, then there is going to be no potential difference, and that is also because of Ohm's law, where if there is no resistance, there can't be any potential difference. We can see this in our graph here, where the potential difference increases across the battery and then decreases across the resistors, and it all goes in a loop. Now, what if we put an ammeter in parallel to our 100 ohm resistor? Well, the resistance is actually going to decrease to 47 ohms from our initial resistor, and our current is going to increase to 0.06 amps. And this is because the current is going to take the path of less resistance. We are assuming that our ammeter does not have any resistance, so no current is going to flow through that other resistor. And then from Ohm's law, current is equal to total voltage divided by total resistance, 0.06. Now let's take a look at an RC circuit and the charge and discharge time of a capacitor. As you charge a capacitor and discharge a capacitor, those times are going to be the same, and the greater the resistance in your system, the greater the charge and discharge time. As the capacitor is charged and discharged, the bulb is going to start really bright, and then it's going to get a lot dimmer. And we're going to see that this is because of that voltage decreases exponentially with time. So we ran this test here where we charged up our capacitor with a 9-volt battery, and we used a 30 ohm resistor. And then in a 20-second interval, we discharged it and found the potential difference at each time. If we take the natural log of the change in potential difference over the initial potential difference, we find that we are able to get a linear value, which is going to be our time constant. If you plot this, then you are able to find the time constant from the slope. So the slope of this graph is negative 0.1673, and that makes our time constant 5.977 seconds. And this is expected, because if you calculate this from the pieces of it, which is a 0.2 Faraday capacitor and a 30 ohm resistor, you get a time constant of 6 seconds. And the time constant is the time in which the voltage drops to 1 over E of the original value. So what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulated one? Well, then the real current would be lower than the simulated current due to real ammeters having a real resistance. So the amount of resistance in your system is going to increase, and that's going to decrease the amount of current running through your system. And what if you were using a real battery and a real capacitor, but no resistor? Even with no resistor in the series, the real charge time is going to be longer than the simulated charge time because all real circuit components have some resistance. You also have to take into account that a real circuit is not an isolated system. Energy in the system is going to be lost to the surroundings, and that's going to alter the readings that you get from your voltmeter and the ammeter.